I watched my neighbor's 12-year-old design and print a custom bracket for his robotics competition last week. The printer cost less than his gaming console. That's where we are in 2026. Budget 3D printers under $300 deliver capabilities that required machines costing $2,000 or more just 5 years ago. These aren't toys. They're entry points to additive manufacturing, the same technology used in aerospace prototyping and medical device production. I'm Kazuki Tanaka, and I've spent over 200 hours testing 7 different models to figure out exactly which budget 3D printers actually build skills that matter for kids. You're listening to the STEM Lab podcast. Quick heads up before we dive in. The research, testing, and script you're hearing are all human-created and verified, but the voice delivering it is AI-generated. Just wanted to be upfront about that. Now, I really appreciate those of you who've been listening for a while. You make this worth doing. And if you're just finding the show, thanks for giving it a shot. I think you'll find we don't waste your time with fluff, just tested recommendations and practical advice for building real STEM capabilities with kids. New episodes come out every Monday, Wednesday, and Friday, so you'll have plenty to work with. Let's jump into today's episode. After running these machines through real-world use in my workshop, I can tell you that some of these printers surprised me. Others disappointed in specific ways you need to know about before buying. So let's talk about what to look for in budget 3D printers for kids under $300. Shopping for budget printers means navigating massive quality differences in a narrow price band. Here's what actually matters. First up, build volume versus footprint trade-offs. Most budget printers offer 180 to 220 millimeter cubic build volumes. That's enough for functional parts, robot components, and most classroom projects. I've found that kids rarely need the full build envelope. They're learning part decomposition and assembly, which is actually better pedagogy than printing massive single objects. The footprint matters more. A printer sitting on a desk becomes a daily tool. One banished to the garage gets used twice, then forgotten. Prioritize machines under 450 by 450 by 550 millimeters if desk space is your reality. Now, enclosed versus open frame safety considerations. Enclosed chambers prevent burns and contain odors, critical for elementary age users. Open frame printers teach more about the mechanics, but require constant supervision. I personally let my 10-year-old operate enclosed machines independently after 2 supervised prints. Open frames, not until 13. Here's my rule. If you won't be in the room during printing, buy enclosed. Period. Moving on to bed leveling systems and first layer success. First layer adhesion determines whether kids persist or quit. I've seen it 100 times. 3 failed prints in a row, and the machine becomes a closet ornament. Auto-leveling systems add $40 to $60 to manufacturing costs, but they're worth every cent for young users. Manual leveling teaches patience and mechanical sympathy, but it also gatekeeps the actual skill you're trying to build, designing and iterating parts. For kids under 12, I strongly recommend auto-leveling. For teens interested in mechanics, manual systems become a feature, not a bug. Professional FDM machines use automatic bed mapping because print technicians need to focus on design intent, not bed tramming. That's the skill we're building. Let's talk about slicer software and learning curve. The slicer is where design becomes machine code. Budget printers typically support Cura, Prusa Slicer, or proprietary software. Cura is industry standard. Learning it at 12 means understanding the same tool aerospace engineers use. Proprietary slicers simplify initial setup, but trap users in vendor ecosystems. I've watched kids outgrow simplified software in 4 to 6 months, then struggle with the transition to professional tools. Start with the real thing.
Next, filament compatibility and ongoing costs. Most budget machines print PLA reliably. PLA costs $15 to $20 per kilogram, enough for 25 to 40 typical prints. Some machines claim PETG and ABS compatibility, but sub-$300 hot ends often struggle with temperature stability above 240 degrees Celsius. Proprietary filament requirements kill learning progression. I refuse to recommend printers that lock kids into vendor-specific spools at 2 to 3 times market prices. The whole point is building capability independence. And finally, connectivity and workflow integration. SD card transfer is clunky but bulletproof. Wi-Fi printing sounds convenient until firmware bugs brick a 3-hour print at 87% completion. I've lived that nightmare. For educational use, I actually prefer SD cards. They force kids to think about file management and physically transfer data. USB tethering is worst case. A kicked cable means lost prints. Cloud-based systems are emerging, but often require subscriptions. For educational environments, go old school. Slice on the computer, save to SD, walk to the printer. That workflow mirrors professional manufacturing handoffs. All right, let's get into our top picks. Starting with the Creality Ender 3 V3 SE. Check the link below to see the current price. This sits at the sweet spot of capability and price for first-time young makers. This is the 2026 iteration of the machine that launched 1 million maker careers, now with auto-leveling, direct drive extrusion, and a 220 by 220 by 250 mm build volume. I ran this through 60 hours of print time with both elementary and middle school users. Here's what works. Automatic CR touch bed leveling removes the biggest beginner frustration. Direct drive extrusion handles flexible filaments that most budget machines can't touch. It's compatible with standard Cura. Skills transfer directly to professional workflows. The open design teaches mechanical literacy and allows hardware modifications. Community support is unmatched. Every problem has been solved and documented online. And the build volume handles 90% of youth projects, including competition robotics parts. What doesn't work as well? The open frame requires active supervision for users under 12. Manual filament loading takes more dexterity than cartridge systems. Build plate screws need periodic tightening, not set and forget, and exposed belts and pulleys are dust magnets if used in shared spaces. The Ender 3 V3 SE is my top pick for teens and supervised younger users because it teaches the actual mechanics of FDM printing. That open frame isn't a limitation, it's a feature for kids ready to understand why designs fail, not just that they failed. Next, the AnchorMake M5C. Check the link below to see the current price. This is the machine I recommend when parents say, "I won't be in the room while they print." Fully enclosed, genuinely quiet at 45 decibels, and idiot-proof with auto-leveling that actually works consistently across different filament types. Print volume hits 220 by 220 by 250 millimeters. The pros: full enclosure with safety cutoffs if the door opens during printing. Genuine auto-leveling that compensates for bed warping over time. AnchorMake Slicer is simplified but exports to standard G-code. Integrated camera allows remote monitoring via smartphone. Fastest print speeds in this price category, 120 millimeters per second practical speed. And preloaded profiles eliminate guesswork for first 20-plus prints. The cons: proprietary slicer limits advanced optimization techniques. Camera requires Wi-Fi and creates privacy considerations for schools. Enclosed design makes it harder to observe mechanical processes. And there's less community modification documentation than the Creality ecosystem. I tested this with 7-year-olds after basic safety orientation. They successfully printed solo after 2 supervised sessions. That's the differentiator. Enclosed design plus software guardrails create independence faster than any other machine I've tested. Moving on to the Sovol SV06. Check the link below to see the current price. This delivers features that cost $500 2 years ago: planetary dual-gear direct drive, automatic leveling, and a surprisingly rigid frame for a sub-$300 machine. Build volume matches competitors at 220 by 220 by 250 millimeters, but print quality edges ahead in fine detail work. What I like: all metal hot end reaches 300 degrees Celsius, handles engineering filaments like PETG and nylon. Dual gear extruder provides precise filament control for miniatures and detailed work.
PEI build plate requires no tape, glue, or adhesion aids. Open-source firmware allows advanced users to customize machine behavior. Linear rail Y-axis reduces ringing and layer artifacts, and maximum 200 millimeters per second print speed when using appropriate profiles. What to watch out for? Touchscreen interface lags during menu navigation. No print resume after power failure unless you install optional UPS. Assembly instructions assume mechanical familiarity, not beginner-friendly. And it's louder than enclosed competitors at around 55 decibels during rapid moves. This is the machine for the kid who's already interested in mechanical systems. I watched a 13-year-old correctly diagnose and adjust belt tension after watching a single YouTube video. The Soval rewards mechanical curiosity rather than punishing it. For younger or less mechanically inclined users, the added complexity creates friction. Now let's talk about the FlashForge Adventurer 5M. Check the link below to see the current price. This is what happens when a company actually watches kids use their machines, then designs accordingly. Fully enclosed, auto-leveling, removable flexible build plate, integrated filament storage, and one-button cloud printing. Build volume drops slightly to 220 by 220 by 220 millimeters. The advantages: completely enclosed with HEPA filtration for classroom use, magnetic flexible build plate, prints pop off with zero scraping or damage. Cloud slicing works on Chromebooks and tablets. Integrated camera and time-lapse recording for documentation. Nearly silent operation at 42 decibels, runs during video calls without interference. And auto pause when filament runs out or tangles. The drawbacks: Flash Cloud requires account creation and internet connectivity. Proprietary filament detection system occasionally throws false errors. Smaller Z height limits tall prints compared to competitors. And advanced settings locked behind expert mode that requires a password. I set this up in a middle school classroom where kids rotated through in 45-minute periods. 0 failed prints due to user error in 30 hours of runtime. The software guardrails work. That same closed ecosystem frustrates advanced users, but that's not the target audience. This is the machine for maximizing successful first experiences. Next up, the Elegoo Neptune 4. Check the link below to see the current price. This one surprised me. I expected corner cutting at this price point. Instead, I found genuine engineering decisions that benefit learning users. Clipper firmware, input shaping for quality at high speeds, dual gear extruder, and auto leveling in an open frame design. Build volume is 225 by 225 by 265 millimeters. What works? Clipper firmware is the same system professional makers use for speed optimization. Input shaping eliminates ringing artifacts even at 200 millimeters per second plus speeds. Direct drive plus dual gear extruder handles flexible filaments reliably. Detailed assembly manual teaches mechanical principles during setup. Compatible with standard Cura, Prusa slicer, and all major slicing tools. And USB-C connectivity for firmware updates and direct printing. What doesn't? Clipper configuration intimidates beginners despite simplified interface. No enclosed option creates safety considerations for elementary users. Touchscreen is small at 4.3 inches, cramped for large fingers. And cooling fan is louder than necessary at 58 decibels during bridging moves. The Neptune 4 is my pick for the kid who wants to understand everything. Setting it up requires following detailed instructions. Loading filament demands understanding the entire material path. That friction is a feature if you're building engineering mindset. For plug-and-play users, look elsewhere.
Last on the list, the Kingroon KP3S Pro V2. Check the link below to see the current price. This is the dark horse. Smallest footprint at 320 by 350 by 410 millimeters total size. But that compact design packs auto leveling, direct drive, and surprisingly good print quality in a 200 by 200 by 200 millimeter build volume. This is the machine for cramped spaces. The benefits: smallest desk footprint in this category, fits on corner workspaces. All metal 300 degrees Celsius hot end handles engineering materials. Core XY motion system is faster and more precise than standard Cartesian designs. Integrated drawer stores tools and spare nozzles. Acrylic panels are available as add-on for enclosure conversion. And budget allows room for filament and tools in the same $300 total. The limitations. Smaller build volume limits large single-piece designs. Core XY mechanics are harder to troubleshoot than standard Cartesian. Community support documentation is thinner than major brands. And cooling is adequate but not optimized for overhangs beyond 55 degrees. I keep this machine on my main workbench because the footprint doesn't dominate the space. Print quality matches larger competitors for 90% of projects. The 10% where build volume becomes limiting? That's when kids learn part decomposition and mechanical assembly, arguably better lessons than printing monolithic objects. Perfect for apartment makers or shared family spaces. Now let's look at technical considerations you need to know about infrastructure, power, and expandability before buying. Power requirements. All machines listed operate on standard 110 to 120 volt North American power. Peak consumption hits 250 to 350 watts during heating, less than a gaming console. None require dedicated circuits. I run 2 simultaneously on my workshop circuit without issues. Connectivity options. SD card readers are universal. USB connectivity varies. Some support tethered printing, which I don't recommend. Others use USB only for firmware updates. Wi-Fi equipped models require 2.4 GHz networks. 5 GHz bands aren't supported on budget machines. Cloud printing requires vendor accounts and introduces dependency risk. Expandability paths. Open frame designs support hardware modifications, different hot ends, print surfaces, direct drive conversions. And closed systems limit physical modifications but often support firmware customization. Budget machines with standard size components like Creality and Soval have massive aftermarket support. Proprietary designs like FlashForge lock you into vendor ecosystems but simplify troubleshooting.
Durability testing. I run budget machines harder than typical home users. 8 to 10 hour daily prints, multiple filament changes weekly, minimal maintenance beyond what instructions specify. V-wheels wear after 200 to 300 hours, and replacements cost around $15 for sets. Belts need tensioning every 100 hours. Print beds warp slightly over time. Auto-leveling compensates. Hot ends clog if cheap filament introduces contaminants. Budget $20 to $25 for annual replacement nozzles and maintenance parts. Safety infrastructure. All machines listed have thermal runaway protection in firmware. They shut down if temperature sensors fail. Open frame models need 18-inch clearance from walls and furniture. Enclosed models still exhaust warm air. Don't enclose them further. PLA printing doesn't require ventilation, but PTG and ABS absolutely do. Offline versus cloud dependency. 3 machines on this list operate completely offline. Slice on your computer, print from SD. 2 require initial internet setup but work offline afterward. 1, the FlashForge, functions offline but loses significant convenience features. For school environments with restricted networks, prioritize offline-capable machines. Let me talk about building progressive capabilities. Budget 3D printers under $300 aren't endpoints, they're entry points to a skill progression that leads to legitimate career capabilities. Here's how I sequence learning with these machines. Months 1 to 2, print discovery. Kids print existing designs from Thingiverse and printables. They learn software workflow, download STL, import to slicer, adjust orientation, generate G-code, execute print. Success rate should hit 90% plus with proper machine setup. This phase builds confidence and intuition about what's printable. Months 3 to 4, basic modification. Introduce Tinkercad for simple parametric changes. Scale objects, add names and text, combine existing shapes. This is where Tinkercad skills become foundational. the same Boolean operations pros use daily. Months 5 to 8, functional design. Kids design objects that solve real problems: phone stands, cable organizers, mounting brackets. They encountered design constraints: overhangs, wall thickness, print orientation. Failed prints become learning opportunities. I see genuine engineering mindset emerge here. Months 9 to 12, system integration. 3D printing integrates with other skills. Design robot chassis that bolt to servo motors. Create enclosures for Arduino projects. Print jigs and fixtures for other tools. The printer becomes one capability in a larger maker tool chain. Year 2 and beyond, material expansion. Graduate to engineering materials, PTG for outdoor components, TPU for flexible parts, composite filaments for specific properties. This requires understanding material properties, not just pushing buttons. Professional makers follow this exact progression. This progression mirrors professional additive manufacturing workflows. Junior engineers at product development firms follow these same steps: design iteration, material selection, print optimization. Starting at 12 with a $250 machine, kids can reach junior engineer capability by 16. That's not hyperbole. I've watched it happen repeatedly. Now, integration with broader STEM learning. These machines don't exist in isolation. I've seen the most impressive learning outcomes when 3D printing integrates with complementary skills. Robotics synergy. Competition robotics teams use 3D printers constantly: custom mounts, protective bumpers, specialized grippers. Kids designing for VEX or FIRST competitions develop stronger CAD skills than those printing novelties. Renewable energy projects. Print turbine blades, test housing designs, create mounting systems for solar panels. Students can iterate designs in days rather than weeks. Programming integration. Generative design and parametric modeling connect directly to coding concepts. Transitioning from visual to text-based programming parallels moving from simplified to professional CAD tools. Both build abstraction and system thinking skills. The strongest STEM labs I've built combine multiple capabilities. A 3D printer plus basic electronics plus measurement tools creates combinatorial learning possibilities that isolated tools don't deliver. Let me address some frequently asked questions. Are budget 3D printers under $300 reliable enough for regular use by kids? Yes, with appropriate expectations. Modern budget machines deliver 80 to 90% successful print rates when properly maintained and used with quality filament. I've run all 6 recommended models through extended testing. Mechanical failures are rare, but user error remains common during the first 20 to 30 prints. The key reliability factor is auto-leveling. Machines without it create significant frustration for users under 14. These aren't toys that break after a month. They're tools that require basic maintenance, like belt tensioning and occasional nozzle cleaning. Professional shops replace nozzles regularly too. It's normal maintenance, not a reliability failure. Plan for around $30 to $40 annually in consumable parts, like nozzles, build surface replacements, and occasional Bowden tubes for PTFE line systems.
What's the realistic time investment for parents supervising 3D printing? Initial setup takes 2 to 4 hours, including assembly, calibration, and test prints. Plan to be present and involved. After that, supervision requirements depend entirely on enclosure and child age. Enclosed machines with auto-leveling require minimal oversight after kids complete 5 to 10 successful prints. I let my 10-year-old run these independently. Open-frame printers need adult presence in the room for users under 13. Each print requires 5 to 10 minutes of prep, slicing, file transfer, machine startup, then runs unattended. I check prints every 30 to 60 minutes for long jobs, but don't sit and watch. Failed prints happen. Dealing with them is part of the learning. Budget 30 minutes weekly for basic maintenance, wiping the bed, checking belt tension, clearing dust. Do these printers require subscriptions or proprietary consumables?
Only one machine on this list, the FlashForge Adventurer 5M, functions better with a subscription called Flash Cloud, but it's optional and free tier works fine for home users. None require proprietary filament. Standard 1.75mm PLA costs $15 to $20 per kilogram from dozens of manufacturers. Avoid any printer that locks you into vendor-specific filament cartridges or spools. You're paying 2 to 3 times market rates for the exact same material. A kilogram of filament produces 25 to 40 typical prints, depending on density settings. Most families go through 1 kilogram per 2 to 3 months with regular use. The real ongoing cost is time and electricity. Each print consumes roughly the same power as running a laptop for equivalent duration. No surprise bills, no forced upgrades, no subscription traps. This is one category where budget equipment doesn't exploit you with consumables.
How do budget printers compare to the $2,000 plus machines used professionally? Professional FDM printers offer tighter tolerances, plus or minus 0.05 millimeters versus plus or minus 0.15 millimeters. Faster print speeds up to 300 millimeters per second versus 150 millimeters per second practical maximums, and more reliable long-run performance. For learning purposes, those advantages don't matter. Kids aren't printing aerospace parts requiring micron-level precision. They're building conceptual understanding of additive manufacturing, design constraints, and iterative development. I've printed the same test object on a $250 Ender and a $6,000 Ultimaker. Visual quality difference is negligible on typical objects with proper settings. Where professional machines win, unattended 48-hour prints, exotic materials requiring precise temperature control, and production runs where dimensional consistency across 100 units matters. For design iteration and skill building, budget machines deliver 85 to 90% of the capability at 10 to 15% of the cost. Professional engineering firms use expensive machines for production. Their engineers learned on budget equipment. Start where the pros started. Can kids transition from these budget machines to professional tools later? Absolutely. That's the entire point of choosing budget 3D printers that use industry-standard workflows. Kids learning Cura on a $250 Creality use the exact same software on $15,000 industrial machines. G-code is universal. Design principles learned printing PLA at home apply directly to engineering polymers in production environments. The progression mirrors learning to drive on a Civic, then upgrading to performance vehicles. Fundamentals transfer completely. I've hired junior engineers who learned on budget machines. Their skill level was indistinguishable from those who trained on expensive equipment. What matters is iteration count and problem-solving experience, not machine cost. A kid completing 200 prints on a budget printer has vastly more practical knowledge than someone who printed 20 objects on industrial equipment. The quality ceiling is lower on budget machines, but the learning ceiling is identical. Professional capabilities come from understanding constraints, troubleshooting failures, and optimizing for manufacturability. All skills these budget machines teach effectively. So, here's the verdict. Budget 3D printers for kids under $300 have reached legitimate capability in 2026. Every machine on this list builds transferable skills that apply directly to professional workflows. For supervised younger users or cramped spaces, the AnchorMake M5C removes friction and maximizes early success. That enclosed safety and simplified workflow gets kids printing independently faster than any alternative.
For teens and mechanically curious users, the Creality Ender 3 V3 SE delivers maximum learning value. Open access to mechanics, massive community support, and compatibility with professional tools creates the richest skill-building environment. The capability you're buying isn't the hardware, it's the iteration cycle. Failed prints teach more than successful ones. Budget machines fail in educational ways. Expensive machines hide problems behind error handling that kids never see or understand. Start printing, start failing, start learning. That's how makers are made.
That wraps up this episode of the STEM Lab podcast. Thanks for spending this time with me.
New episodes drop every Monday, Wednesday, and Friday, so you've always got something coming. If you found this helpful, I genuinely appreciate it if you'd leave a 5-star rating and maybe write a quick review. It's honestly the main way other people find the show, and it helps more than you'd think. And make sure you're subscribed or following so you get notified the second a new episode goes live. I'll talk to you in the next one.